Good afternoon, everyone. This is the last part of motion in 2D, and that is known as circular motion. Though we are officially starting it today, but I think from the very first day, we have done some problems on circular motion. In fact, the first problem that we did on distance and displacement, it was about circular motion. Yes or no? Do we remember it? Particle was moving, we found out its displacement, we found out its distance. So now we will try to study circular motion as a separate topic, and we'll see how things turn up in this topic. Now, first of all, before moving on to circular motion, what do you understand by a circular motion? Can anyone tell me what do you mean by circular motion? What do we understand by the term circular motion? Can anyone tell me? What do we understand by the term circular motion? Yes. Tell me. Yes, beta. Why when sir speaks, the voice is clear. When you speak, the voice doesn't come. Why is that so? I only get half of your voice. Still nothing I hear.
Circular path.
Circular path. Okay. Circular motion means circular path. But what do you understand by circular path? Okay. Every circle has a center and every circle has a radius. Now, if I have to define what is a circular motion, I can obviously say a particle moving on a circle is circular motion. That is one way of defining it. But it is also good to understand what is a circle. So I can write this, understand this circular motion in this way. If a particle moves in such a way, if a particle moves in such a way, that what? In such a way that its distance from a fixed point remains same. Then we say that the particle is following circular motion. Now, what is this fixed point known as? What is this fixed point from where its distance remains constant? What is this fixed point known as? Can anyone tell me what is that fixed point known as? I can't hear you, but I hope you understand that that fixed point is known as this O, which is nothing but the center of this circle. We understand this, yes or no? The center of this circle, that fixed point is known as the center of this circle. What about the fixed distance? Its distance remains same. So what is that fixed distance known as? I hope you understand that the fixed distance from the distance which remains fixed is known as the radius of the circle. So every circle has a center and every circle has a radius. Now, once you have understood this, we can also write if a particle moves on a circle, the motion is known as circular motion. So basically, if a particle moves on a circle, the motion is known as circular motion. Now, the question is, why we have to read it as a separate topic? If you remember, we had done some questions where the particle was moving on a semicircular path. We had found out its distance. We had found out its displacement. We had done that already. We have done motion in 2 dimensions. The question arises why we have to study it as a separate topic. What is different that we are going to study here? There is nothing different. Frankly speaking, that we are going to study here. There is nothing different here. But the only thing is we are going to study it in a different way. How are we going to study it in a different way? Now, suppose this is your circle. As I said, every circle has a center and every circle has a radius. O and R. Now, we've studied this motion before. What are we going to do different here? Now, suppose if a particle is moving on a circular path and we know that in advance that it is moving on a circular path. If someone asks you, how will you give the position of that particle? The one way of giving the position of the particle, let us say the particle P is here, we can always make our, we can always make our one axis as x-axis along this line with the center or origin here, and I can make my y-axis along this line with the center at the origin. Now, if someone asks us how do you find out the position of this particle, you can very easily say, it is not a problem. I will find out this x coordinate and then I will find out this y coordinate, and I can say that the position of this point P is simply x comma y. Not a problem. We have done this. Or the other way is I could also draw a position vector r vector joining the origin to the point P, and I can say this r vector, the position vector of the particle, is nothing but xi plus yj. I can easily do it this way. We have already done this. Knowing the x and y coordinates, we can easily locate the position of any point on this circle. So far, so good. What is different here? I mean, why can't we do it this way, and why we have to study it as a separate topic? I hope everyone is noting it down. I hope everyone is noting it down. Okay. Now see, I can do this in a different way. And what is the benefit that we are going to get in this different way? Let me just make it correctly. I can do the same thing in a different way. Since I know beforehand, what do I know beforehand? I know beforehand that this particle is going to move in a circular path. No matter this is my x-axis, yes. No matter this is my y-axis, yes. No matter this is my origin, yes. Now, instead of telling you the x and y coordinates, I know that the point P is here. The point P, or the position of the particle, is going to remain on this circle. Now, instead of telling you the x and y coordinates, I've already told you where the center of the circle is. You already know the center of the circle is. Instead of telling you the position coordinate, what do is I tell you this angle theta. I tell you this angle theta with the x-axis. It's always said with the positive direction of x-axis. Let me say this angle theta from x-axis. You already know that the distance of this point or distance of this particle from origin is r. So instead of telling you x and y coordinates, I can also say that the position of this particle can be given by this one, r and theta, where r is the radius or the distance from the center, and theta is the angle that it makes with positive direction of x-axis. I can do that, yes or no? I can give the angle from y-axis also. I can give from negative x also. I can give from negative y also. But normally it is given from positive direction of x-axis. This is your x-axis and this is your positive direction. I can also give you the position of the particle like this. Now, the benefit of doing it this way is whenever the particle is, wherever the particle is, now sometimes it can be here at this point Q, sometimes it can be here at this point R, sometimes it might be here at this point S. R is always fixed. And if I tell you R, I just have to tell you the value of angle theta, and you should be able to find out where this particle is, yes or no? So this is a better way to understand the position of this particle in terms of r and theta. Whenever this position is given in terms of r and theta, we call it the polar coordinates. If the position is given like this, we call it the polar coordinates are given. And whenever the position is given like this, we call it the Cartesian coordinates because it is given in the form of x and y. So this is the Cartesian coordinates. R and theta are known as your polar coordinates. Cartesian coordinates, polar coordinates. So polar coordinates is the one that we are more concerned about because this x and y thing we have already done. Now, in this, there are two things. One is r, radius. We already know the radius. The other thing is this angle theta. The most important aspect here, apart from r, is angle theta because this angle theta tells us actually where the particle is. Because r, only r cannot tell you. R is fixed. Radius of the circle is fixed. You know the distance. But the entire thing depends on this angle theta, and therefore this angle theta, since it is angle, this angle theta is known as angular position of the particle. Angular position of the particle, and that is the first thing, first heading, first definition that we have to understand is the angular position of the particle. Now this angular position of the particle is given by the angle theta. Now remember, it tells us the position of the particle in terms of angle. In terms of angle, it is normally given with positive direction of x-axis. That is how it should be told, but we may call it, we may give the position from y-axis, we may give it from negative x also, but normally it is given from positive direction of x-axis. Now, since it is an angle, the SI unit is radian, not degrees. You must understand this. SI unit is radian. It is dimensionless because I told you that angle is dimensionless. Do we understand this? Can I have raise hands from everyone that we understand this? It is dimensionless. It is a scalar quantity. It is a scalar quantity. Apart from this, what is the other thing that you have to understand? Have you written this, everyone? I'll give you 2 minutes. Write this down. Write it down quietly. I understand them. I'll give you 2 minutes.
Sir, can you take it?
Everyone done this? Boys? Girls? Okay. Now we follow a small sign convention here. And it is good that we understand the sign convention here. If we go back to motion in 1D and 2D, along x-axis, positive x was positive and negative x was negative, taken as negative. Positive y was positive and negative y downwards was taken as negative. Here is also a small sign convention that we take, and you must remember this sign convention that any angle which is anti-clockwise. Understand the meaning of anti-clockwise? Opposite to the direction of clock. Anti-clockwise angles are taken as positive and clockwise angles are taken as negative. Clockwise. So this angle from the x-axis, it is positive. So this should be called as positive theta. If the point was here, point S, this angle would be like this. So it will be called negative angle. Do we understand this? If the angle from the axis is in the anti-clockwise sense, it is positive. If the angle from the axis is in the clockwise sense, it will be called as negative. So we use the sign convention for this angle, plus and minus. Do we understand this? Remember this sign convention, because this sign convention is what we are going to use throughout this chapter. Have you noted this down? Okay. Now, what is going to happen, and I keep on moving with the same diagram, this particle is not going to remain at point P, because if it always remains at point P, it is at rest and there is no motion. Obviously, this particle is going to move. At some times, it's going to be at point P. At other times, it might be at point Q. So the particle has changed its position. Now, instead of calling it position, we will call it the particle has changed its angular position. Do we understand this? The particle has changed its angular position, and therefore comes the next term. Can you tell me what is the next term that is going to come? The first term was angular position. Now the particle has changed its position. What is the second term that is going to come? And the second term that is going to come is anyone?
Displacement.
Not displacement, dear. Not displacement, dear. Angular displacement. Because we'll again talk of this displacement in terms of angle. Delta theta is the term that we are going to use. Delta meaning change, theta meaning angle. So how will I define it? It is basically change in angular position. It is the change in angular position. As soon as we use the word change, delta comes, delta theta, the change in angular position would be final angular position. You can call it theta 2 minus theta 1, which is the initial angular position. So far, so good. Do we understand this? Angular position. Now again, since it is change in angle, the SI unit remains same. SI unit is radians. It is again dimensionless because it's an angle, change in angle, it is dimensionless. What type of quantity is angular displacement? Now that is what you have to listen very carefully. For large change, when there is a large change in angle, whenever we say large change, that means delta theta. Delta theta means it's a large change in angle. For large change, which is delta theta, it is taken as a scalar. Large change, if the change in angle is large, 5 degrees, 10 degrees, 15 degrees, it is taken as a scalar. It is not taken as a scalar, it is a scalar. But for small change in angle, now whenever I use small change, this is d theta. This d theta is a vector. Now the question comes, why this is a scalar and why this is a vector? I will leave you to find out. Find out why. Does anyone know why? Well, if you don't know, find it out. Why large change in angle is taken as a scalar quantity and small change in angle is taken as a vector quantity. I will leave that to you. So delta theta is a scalar, but d theta is a vector. So far, so good. Have you understood this? But let me understand, theta is always a scalar. Theta is not a, there is no doubt about theta. Theta is a scalar. Delta theta is a scalar also. D theta is a vector. So far, so good. Do we understand this? Now remember, we have started circular motion and we have seen two terms here, angular position and angular displacement, theta and delta theta or d theta. Now these two terms, does it remind you of something that we have already done in the past? This motion is known as circular motion. The motion that we were doing, 1D motion in the past, that was known as linear motion. Does this angular position and angular displacement, these type of terms, remind you of something in the past that we had done? If you understand that, you will understand what is the next term that is going to come. Yes? Anyone? Angular position, angular displacement, does it remind you of anything?
Velocity.
What, bacha?
Velocity.
It reminds you of angular velocity. No, I'm telling you, angular velocity I have not even said once. Angular position and angular displacement, does it remind you of something else? Angular displacement, if I just rub this part, it becomes what? Displacement. And that is the term that it is actually similar to. The term that we had done in 1D and 2D motion, delta R. But there, that displacement, delta R, change in position vector was always a vector. So whatever we had done in the previous chapter, same things are going to come here. The only difference between them is one difference is whether they are scalars or not, whether they are vectors or not. The other difference is they are in terms of angle now. So everything will have angular added to it. Angular displacement, delta R vector becomes angular displacement. And remember that position vector. Do you remember that position vector? This position vector, this angular position vector was giving us the position of the particle. And as you can see here in the diagram also, this R vector tells us the position of this particle P. This angle theta is also telling us the position of the particle P. They are obviously doing the same thing, but in different ways to be seen. Do we understand this? Angular position is same as position vector. The only thing is one is a scalar, the other one is a vector. One is an angle, the other is a vector. Angular displacement is similar to what we had seen position vector. The only difference being whether it's a scalar or not, whether it's a vector or not. Having said that, what should be the third term that should come? If you understood these two terms, what is the third term that should come? Yes, tell me, what is the third term? The first term is angular position. The second term is angular displacement. What, my dear friends, is the third term? Anyone?
Velocity.
Again, your voice, half voice I hear, and half I have to guess. Girls, I mean, your mic is probably more clearer than the boys' mic. Can you tell me what is the next thing that is going to come? I only see chi.
Angular velocity, sir.
The third term that is going to come is average angular velocity. Average angular velocity. So if you understood, or if you don't even remember the previous terms, now it's a quick revision of those previous terms. Average angular velocity. Average is always dabba and angular velocity is omega. This is not W beta. This is omega. It's a Greek alphabet. Small omega, we call it omega. Now, what does this term remind you of? Average angular velocity. This average angular velocity is doing the same thing in circular motion as your average velocity was doing in the linear term. The only difference being this is not a vector, this is a scalar. Average angular velocity. Now, can you tell me what will be this average angular velocity? If you remember average velocity, you should be able to tell me, bacha, what is this average angular velocity? Anyone? Yes, I'm waiting. It will be equal to total. I've written one word, total.
Total
Total angular
displacement by time.
divided by total time. That would be your average angular velocity. Do we understand this? Yes or no? No or yes? Now, since we now know, I can write this average angular velocity as delta theta, total change in angular position, angular displacement, divided by delta t. You can also write it as theta 2 minus theta 1 divided by delta t or t, whatever. Now, since this is delta theta divided by delta t, my dear friends, it is a scalar quantity. Its SI unit would be radians, rad per sec, radians per second. Dimension, this has a dimension, and its dimension would be t minus 1. Average angular velocity. Do we understand this? Yes or no? No or yes? Average angular velocity, it's a scalar. Now again, we will use a sign convention for this. And you already know the sign convention. It depends on delta theta. If delta theta is positive, average angular velocity would be positive. Can you tell me what is the next term that is going to come? Everyone has written this down? Again, this is a revision of what we have already done.
Angular acceleration, sir.
Now remember this average angular velocity. Let me just give you one more point. This average angular velocity is always calculated over an interval of time. It's always calculated over an interval of time. Between A to B, between T1 to T2. It is always calculated over an average, over an interval of time. Now I repeat my question again. What would be the next term?
Angular acceleration, sir.
Average angular velocity is calculated between 2 points over an interval of time. What is the next thing that will come? The next thing that will come will be known as, you don't seem to remember anything. That is not a good sign. The next thing that will come is instantaneous angular velocity. Denoted by omega, and this is a vector. Instantaneous angular velocity. Now I may ask, which type of term is it similar to that we have already read? It is similar to what? No idea? It is similar to instantaneous velocity. Velocity at any instant was instantaneous velocity. So what is instantaneous angular velocity? This is the angular velocity at any instant. If someone is moving in a circular path, circular motion, and the other person asks him, what is your velocity? What is your angular velocity? He will tell his instantaneous angular velocity. Do we understand this? Yes or no? No, yes. Now, how will I write this instantaneous angular velocity? This is omega vector, because this is d theta, which is a vector, divided by dt. Angular velocity at any instant, or you can also call it, so it is d theta by dt, rate of what? Rate of what? Yes, beta? Rate of change of angular position with time. Do we understand this? Rate of change of angular position with time. Again, it has the same unit. What type of quantity is this? Scalar or vector? This is definitely a vector quantity. It is a different type of vector though, and we will discuss those different type of vectors after some time when we get further ahead in life. Not right now. This is again a vector quantity. Instantaneous angular velocity. Do we understand this? Yes or no? What is the next term that is going to come? What is the next term, bacha, that is going to come? What is the next term that is going to come, bacha? Huh?
Angular acceleration.
Angular acceleration. No, the next term that is going to come is uniform circular motion. The next term that is going to come is uniform circular motion, UCM. And in most of the cases, not in this chapter, but in the chapters that are going to come in your 11th standard and 12th standard, you will encounter this UCM very often. uniform circular motion. Now, this is the time that I'm going to ask you, what is this UCM, uniform circular motion? When will you call circular motion as uniform? If the angular velocity of the particle what happens with the angular velocity of the particle? If the angular velocity of the particle remains same or constant with time, then the motion is known as UCM. Then the motion is known as UCM. Now, if this happens, then what will happen? Your average angular velocity will be equal to your instantaneous angular velocity. I'm writing here magnitude because average angular velocity is a scalar and instantaneous angular velocity is a vector. So your angular velocity is going to remain same. It is going to move with a constant angular velocity. Angular velocity remains same or constant. Do we understand this? Now, what does this uniform circular motion should remind you of? This uniform circular motion should remind you of, it is similar to motion with uniform velocity. If you remember the motion with uniform velocity, we used to call it uniform motion, motion with uniform velocity, uniform motion. The velocity was constant there. Here, angular velocity is constant. There, the velocity was constant, particle was moving in a straight line with the same speed. Here, motion is circular, so it cannot move in a straight line. It will move in a circle, but it will move with constant angular velocity. Do we understand this? Or this has gone above our head saying bye bye, bye bye, bye bye, sir. I'm going. Don't worry about me. I'm gone out of this room. Do we understand this? So everything that we are doing here in this particular chapter is a replica of what we have already done. Uniform circular motion is exactly similar to your uniform velocity motion, not in terms of the motion, but in terms of the topic. Now, as soon as we hear the term uniform circular motion, then the next term comes, and that is under your uniform circular motion. The next term that comes is known as the time period of UCM. Now, remember, this time period is only defined for a UCM, because if the motion is not UCM, the time period does not exist, because denoted by the capital letter T. Tell me, my dear friends, you must have heard about this term time period. Tell me what is time period. Remember, it is only defined for UCM. Tell me what is time period. 1 minute. You must know this. Even if you don't know it, make a definition now. And tell me, what does time period T mean to you? Tell me fast. Huh? Fast, fast, fast. No one knows this? Yes, yes, I'm waiting. What do you understand by the term time period, my dear friends?
If a particle comes to its
the body comes to its
initial position.
not a very good way of saying that same thing. The better way of saying the same thing is time taken to complete what? One rotation, if it is rotating, or one revolution. if it is revolving, or time taken to complete one full cycle. Do we understand this, or this has gone above it saying bye bye, bye bye, I'm going, bye bye. Time taken to complete one revolution, one circle. What is the time period of rotation of Earth? What is the time period of rotation of Earth? And this is a standard fourth question. My kid knows it. How much time Earth takes to complete dung 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 dung? How much time it takes? Huh? No one knows this also. 24 hours is the time period of rotation of Earth. What is the time period of revolution of Earth around the sun? 365 days. Time period. Time taken to complete one cycle, one rotation, one revolution. What is the time period of the second hand of your watch clock? The time period of the second hand is 1 minute. 1 minute it takes to complete one circle. What is the time period of your minutes hand of your clock? 1 hour. In 1 hour it complete dung 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 dung. What is the time period of hour hand of your watch? 12 hours. 12 hours take to dung 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 dung. That is your time period. Do we understand this? Yes or no? It has gone above it saying bye bye, I'm going. Chalo. Now there is a relation between time period and omega, because omega is constant, and this is the revolutionary relation. T is 2 pi by omega. 2 pi is the angle it completes in one revolution. 2 pi means 360 degrees. Remember, angles are always said in radians and not degrees, my dear friends. Do we understand this? Yes or no? Chalo. So there is hope. Time period is 2 pi by omega. As soon as you come across time period, that is the second term that is going to come. What is the second term that is going to come? Oh, sorry. What is the SI unit? I must not tell you. What is the SI unit of time period? Tell me fatafat. Huh? We don't know it, sir. Oh, yes, we know it. Seconds. What is the dimension? It is time period. So dimension has to be t raised to the power by not -1. T raised to the power 1, or t simply. Oops. Do we understand this? Now, as soon as we come across time period, the second cousin brother of this time period comes. And the cousin brother of this time period is known as frequency. This is the cousin brother of this thing, and it is normally denoted by small f, not capital F. Now, what is this time? What is this frequency, my dear friends? Whatever, tell me the definition. We don't know it, sir. This is the first time we are reading this term, sir. Make a definition now. What is frequency? Tell me fast, tell me fast. Number of revolutions or cycles per second. In 1 second, how many times are you moving in a cycle? That is known as frequency, my dear friends. Will you remember it now? Yes or no? No or yes? Then the relation between frequency and time period. Frequency is 1 by t. Do we know this? Frequency is 1 by t. Frequency is 1 by t. Now t is 2 pi by omega. So I can also write frequency as omega divided by 2 pi. Or I can also write omega as 2 pi f. So this is all the relations written together. Do we understand this? Yes or no? No or yes? Or this is gone above and saying bye bye. What is the SI unit of frequency? Hertz. Have you heard this? Hertz. 1 hertz is 1 revolution per second. What is the dimension of this frequency? t raised to the power minus 1. Do you understand this? Yes? Or it has gone above what I'm saying? No. I'm not worried. I'm going. Okay, we are worried. We are going. Now, here is a very important thing that you must understand from this block. Oops. From this block, as you can see, omega here is angular velocity. F is frequency. Now, F is definitely your frequency. Omega, my dear friend, is definitely nothing but an angle. Omega is an angle. So basically, to get the value of omega, I have multiplied one angle with frequency. Angle, frequency, angle, frequency. Therefore, I can call this omega by a new name. Not in this chapter, but in the chapter that are going to come, we may not call omega as angular velocity. Angle, frequency, angle, frequency. We are going to call it what? Huh? We are going to call it angular frequency. So angular frequency means nothing but it actually stands for your angular velocity in that case. But when we go ahead in the chapter on waves, the chapter on SHM, it may not be angular velocity, it would be angular frequency. But both of them mean the same thing. Do we understand this? They mean the same thing. That is what you have to understand. So what we have seen angular velocity, average angular velocity and instantaneous angular velocity. And we have seen that if your angular velocity remains constant, that motion is known as uniform circular motion. And whenever we talk about uniform circular motion, we talk about time period, we talk about frequency, we talk about angular frequency, because all of these things are constant. Do we understand this? Yes or no? Here is one question. Let's see if we can do this. Simple question. Questions are pretty damn simple, my dear friends. Can we have the answer for this one? Oops, where is this one? A particle completes 1.5 revolutions in a circular path of radius 2 centimeters. What is the angular displacement of the particle? What is the angular displacement of the particle? You have 2 minutes. Yes, my dear friend, anyone has an answer? Huh? No one knows it? Shall I do it?
Sir,
Yes, beta? 3 pi is correct. 3 pi. I've already told you, one revolution means, watch, one revolution is equivalent to an angle of 2 pi. So how much is 1.5 revolution equal to? The angular displacement in that case would be equal to 3 pi. Do you understand this? In terms of angle, how much angle it had turned. Do you understand this? Yes or no? Okay. Chalo then, since the time is over, we have introduced ourselves to some terms. In the next class, we'll introduce the next character in the story. Now, this next character in the story is going to change your angular velocity, and that character would be known as what? Huh? That character will be known as what? Angular acceleration. So that's coming up in the next class. I'll see you there. Please go through what we have discussed. I'll send you sheets that you can do. So concentrate on those sheets. Okay. Take care.
Bye, sir.
Bye bye, beta.
Take care.
Bye, bacha.
Thank